In this video, we will have a look at how we can sample a signal and describe it as a vector. And then we will use the discrete Fourier transform to analyze the frequency content of this vector and look at some of its properties. In particular, we will give an example of how a channel described by an FIR filter or finite impulse response filter is creating intersymbol interference, but we can untangle that interference using the discrete Fourier transform. The signals that are showing up in wireless communications are continuous signals, but we are typically taking discrete samples of them when they are reaching our receiver. And here's an example of this. I have the time axis here, measured in milliseconds, and the true signal might be this blue one here that is oscillating up and down. And then we are taking samples of this signal with a certain sampling rate, for example 1 kilohertz in this case, where we are taking one sample every 1 millisecond. So we have a sample here at millisecond 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these samples are then stored in a vector, describing our signal in the discrete time mode. And now we only have the samples. The actual notion of the absolute time here, how much time it were between the different samples, is important from a practical perspective, but when we are analyzing the signal in terms of this vector, we don't need to remember exactly what was the sampling rate and what was the frequencies that we were having in the original signals. However, it is important to satisfy the sampling theorem when we are sampling signals and would like to analyze their content afterwards. So the sampling theorem is saying that we can get a complete representation of a signal. We can reproduce it, and therefore our sample contains all the information if a particular thing is satisfied. Namely that the sampling rate should be greater than 2 times the highest frequency or the bandwidth of our signal. This condition is satisfied in this example, which means that when we have the samples and we would like to create a continuous time signal that goes through all of these different points, well then the blue one here can be exactly created again. However, there are also other kind of signals that would go through these points that contains much higher frequencies, and those signals we cannot really tell them apart. But as long as we know that this sampling theorem is satisfied, well then this signal vector is a complete representation of the signal. In this video, we will continue looking at how we can analyze the frequency content of a signal like this. And that is done based on the discrete Fourier transform. So say that we have taken a certain number of samples, S samples. So then we have a discrete time sequence, chi0 to chi s-1. This is the kind of indexing that we will use in this video. The discrete Fourier transform, or DFT, is another sequence of the same length, chi bar 0 to chi bar s-1. So the bar here is denoting that this is the Fourier transform. And it is supposed to describe the frequency domain content, the different frequencies that exist in our time domain sequence. And we will see in a moment exactly how that is done, but the important thing is now its definition. We are computing it individually for each of the different elements here in our sequence. We are summing over all of the time domain sequences. We take each one of them and multiply them with a complex exponential. E to the power minus j2 pi s, which is the summation index, nu, which is the index here in the frequency domain, and then we divide with the number of samples that we have in our sequence. And then we are multiplied with 1 divided by the square root of s. If you have seen the discrete Fourier transform before, you might have not seen this scaling factor here, because different textbooks are providing different scaling factors. But in the wireless communication area, it is important to include this 1 over the square root of s term, because then we make sure that if we are summing up the absolute value squared of the time domain sequence and the absolute value square of the frequency domain sequence, well then they are always identical to each other. That means that we can measure signal power in both time and frequency, and the value will be the same. Since we are considering one sequence that we can put in a vector, and another sequence that we can also put in a vector, then there should be a transformation between them described by a matrix. So we could describe the entire discrete Fourier transform process as a vector transformation to another vector using a matrix. And that particular matrix, called the DFT matrix, will contain this 1 over the square root of s term and this e to the power of something at the different entries of the matrix. So this is an S by S matrix, so we can take an S-length vector and produce an S-length vector. And it contains ones in the first column and first row, and then it contains different exponents of a variable here, which is a complex exponential, e to the power minus j2 pi over s. And remember that the complex exponential is a cosine of the same argument minus j times the sine of the same argument here. Or the minus sign is the one that is providing the minus sign over here. So this complex exponential is taken to different exponents in different entries here in the matrix. And when we are taking something to different exponents, we are essentially changing the argument here. So we are changing the frequency that we are considering in the cosine and the sine terms. The mapping between the time domain and the frequency domain vectors here is unique. And that can be seen by the fact that this f of s matrix is invertible. So we can move it back and forth here, and we can transfer from time to frequency or from frequency to time just by using the inverse of this one. In fact, f of s is a so-called unitary matrix, which means that each column here have a length or a norm that is equal to 1, and that the different columns are also having inner products that are 0. So that means that these different columns, or also the rows here, is a orthonormal basis of a vector space. Based on this matrix vector representation, we can also define the inverse discrete Fourier transform. Then we take the chi bar vector, we multiply with the inverse of the DFT matrix, and then we get the chi vector back. And since this f of s is a unitary matrix, taking the inverse is the same thing as taking the conjugate transpose on it, which makes the operation simpler. And now comes the interesting thing. How can we generate this signal based on its frequency domain content, and what does it mean to have a frequency domain content? Well, if we are looking at this discrete Fourier transform matrix with the conjugate on it, then this is a way of representing it when we have a sequence length of 7. So here we have the frequency domain content, and it will be a complex vector in general. Then I have shown here the different values that we're having in this matrix. And how do I show them? Well, based on that there is sort of an amplitude that is varying here horizontally. We have the solid lines, which are the real part, and the dashed lines that are the imaginary parts. In the first column, we see that the value is always the same, both for the real part and the imaginary part. In the second column, the values are taken by sampling a sinusoid with a particular frequency, and we see that we have a cosine in the real part and we have a sine in the imaginary part. Then in the third column we also have a cosine and a sine, but now you can see that the oscillations are faster because now we have a larger frequency. In the red part here we have yet an even larger frequency, and then the same frequencies are coming back in the last 3 columns. So the color here is showing that we have the same frequency here and here, but the curves are shifted, as you can see. And the purple one here we also have a shifted and complex conjugate, and the blue one is also having the same frequency as this blue one, but we have a shift and conjugate. So what is then the interpretation now? Well, this time domain sequence that we are generating is obtained by taking these elements that are describing how much of this constant signal we have, how much we have of this blue signal with a particular frequency. Then in chi bar 2 we are saying how much of this pink signal we're having. Then in chi bar 3 we see how much of this red frequency we are having in our time domain signal, and then it continues with the same frequencies but with different shifts and conjugates. So we are actually generating the time domain sequence based on a linear combination of different frequencies and cosines and sines of those frequencies. So that is why the discrete Fourier transform is actually describing the frequency content, signals of these frequencies. And more generally, we can call the columns of this conjugate transpose of the DFT matrix, which we can also call the I-DFT matrix, since it is the inverse discrete Fourier transform matrix like this. These columns are basis vectors in the vector space, the complex vector space of dimension S. And they are representing frequencies. So we can actually represent a vector of dimension S using any choice of basis vectors in linear algebra, but this DFT matrix is providing a natural type of basis vectors because they are describing signal frequencies. I will now provide an example of when the discrete Fourier transform is very useful when considering communication systems. And this is a communication system where we are sending an input signal to our system, chi of k, where k is a discrete time index. And then the signal, when it's reaching the receiver, is processed by a filter, and finite impulse response filter, which is described by this impulse response of length t plus 1, h0, h1 up to h of t. And what does it mean? Well, what we are having here at our output is chi of k multiplied with h0. So this is the signal that we are transmitting right now, and here we see the attenuation and potentially the phase shift that that signal is getting before reaching the receiver. But then we also have delayed copies of our signal that is reaching it. So we have a memory of length t in our channel. So we have a one delayed copy of the signal multiplied with h1 that is added to the received signal. Then we have a 2 time step delay, and we're multiplying then psi k minus 2 with h of 2. And then we go on like this until we have the last component here, psi k minus t, that is multiplied with h of t, and we add it to this one. So we can write our output signal, y of k, as a summation over signals that we are transmitting. The signal that we are transmitting right now have a L equal to 0 here as the index in the summation. So then we get x of k minus 0, so x of k. And then we are multiplying it with h of 0. And then for h of 1, we have x of k minus 1. And we go all the way in the summation to t, where we get h of t multiplied with x of k minus t. So this is a description of what is going on in this FIR filter, or finite impulse response filter. The shape of this received signal can also be written with this notation. It is a linear convolution between the sequence of the signal that we are transmitting and the sequence with the impulse response. So this is the typical notation of it. If we start to transmit at, say, time 0, then what will actually happen before time 0? Well, when we are transmitting chi 0 here, there will be delayed copies of the transmitted signals still in the filter. So how do we really start our communication? Should we transmit 0 for a while, or should we transmit something else? Well, there is something clever that we can transmit before we start our transmission. So suppose we would like to transmit chi 0 to chi s minus 1. So this is an input sequence of length s. And we know that what we receive at time 0 and maybe at some other times will contain old copies of the signal. So we would like to control what was transmitted before our data transmission actually started. And a clever way of dealing with that is to add a so-called cyclic prefix. So if we have a sequence of s symbols, then we take our last t symbols, so obviously s must be greater than t, and we copy them first. So we are making sure to transmit some of our data before we were actually starting our official transmission. So chi at time minus 1 should be the last symbol here, s minus 1. And then we have chi of minus 2 should be s minus 2, and down to chi of minus t should be chi of s minus t. So this is a cyclic prefix because it looks like the signal is just continuing over and over again in a cyclic manner, because in the beginning we have the same thing as in the end. So if we are considering now the output signal that we're having, but we only care about the output that we're getting during the time when we're transmitting our supposed data here between 0 and s minus 1, then we can write that as a summation, just as before, of the impulse response, multiply with x. But when x has a negative number here, we should add s to it, so that we are taking symbol from the end of the sequence instead. And this is expressed by this notation here. K minus L modulo S means that when we have something that is not between 0 and S minus 1, we are adding or subtracting S from it in order to get something in that range. In this case, we are considering sometimes negative numbers, and in those cases, we are adding S to it, so we are getting the terms here at the end. And when we have a received signal that looks like this can be also written as a convolution between the input sequence and the impulse response. But it's not a linear convolution as before, but a so-called cyclic convolution, because when xi of negative numbers are considered, they are not 0, but we are instead adding s to them, so we are taking something at the end here of the sequence. And why is this of interest? Why did we make this whole thing up? Well, there is an important relation that one can establish using the discrete Fourier transform. So if we are taking this output signal here and we compute its DFT for the sequence that we are getting for k goes from 0 to s minus 1, then the Fourier transform y bar of nu, where nu goes from 0 to s minus 1, is the product of something that is a discrete Fourier transform representation of the impulse response and the DFT of the input sequence here. We already know how to compute the discrete Fourier transform of the input sequence and the output sequence, but the discrete Fourier transform representation of the impulse response is computed slightly differently, and it's defined down here. So it is the summation over all of the components in the impulse response, and we multiply with e to the power minus j2 pi s nu divided by capital S, the number of samples that we're having in our sequences. But we should notice that the summation here is not going up to s, but only to the number of coefficients we have in our impulse response. And importantly, there is no 1 over square root of s term in the DFT representation of the filter. So why is this whole thing of interest? Well, we had a complicated channel where we're sending an input sequence, and then we get a received signal, an output, that was a summation over a lot of different signals multiplied with different so-called channel taps from our FIR filter. But if we just compute the discrete Fourier transform of everything, we get a very simple channel instead, where we send one input, we get one output, and the input is just scaled by a factor here coming from this discrete Fourier transform. So this is something that's very convenient when designing communication systems. And to look a bit deeper onto it, we can also make use of our matrix representations. So here we have the vector describing our input sequence. Here we have the vector describing our output sequence. And then we can describe the entire FIR filter when we are including the cyclic prefix using this matrix here. So chi0 is multiplied with h of 0. And then h of 1 is multiplied with the last signal in our sequence, h of 2 with the second last, and so on. And in this example, t is equal to 3, so this is the last component in our impulse response. Then when we are transmitting the second time, now we transmit chi0, we multiply with h of 0, then we have a delayed copy here of the first signal, multiply with h1, and then here we have the components coming from the cyclic prefix. And then it goes on like this. This is a matrix where we have a main column always containing h of 0, a subcolumn with h of 1, h of 2 in the next one, and so on. So this matrix have a particular circular shape, where each row is obtained by the row that we have above it by just shifting everything one step to the right in a circular manner by moving the thing that is moving out to the right to the left-hand side. When we are then computing the discrete Fourier transform, we are transforming the whole thing into something that looks much simpler. So the chi vector here is turned into the frequency domain vector like this, and the frequency domain version of the y vector is this one. And then the only matrix that goes in between here is a diagonal matrix now containing this frequency domain's representation of the impulse response, which we also call a frequency response. So the way that this is utilized in communication systems is to know that we're always transmitting in the time domain and we're always receiving signals in the time domain. But by using the discrete Fourier transform, we can transform the system when we are transmitting one block into a frequency domain representation that is very simple. We transmit one signal in the frequency domain, we get one signal in the frequency domain, there is no interference between them, in contrast to what is happening here with all the intersymbol interference with delayed copies that appears in the time domain. So this is, for example, used in orthogonal frequency division multiplexing, or OFDM, in order to turn a channel into orthogonal frequency components called subcarriers. And as a final thing, we can also notice that there is an important relationship between the so-called circulant matrix that we're having here when we are representing the FIR filter and this diagonal matrix like this. Remember that the chi vector is the inverse Fourier transform matrix multiplied with chi bar, and y is in the same way computed from y bar. Then we can observe that this matrix here must be equal to this diagonal matrix here, but with the Fourier transform matrix on the right and left hand side. So this is essentially a eigenvalue decomposition of this matrix. So the eigenvectors is obtained from the IDFT matrix when we're having this type of circulant matrices. So whenever we have a channel described by an FIR filter, we can always add a cyclic prefix in front of our transmission of a block of signals, and then we can turn the whole thing without loss of any other generality into the frequency domain and communicate using independent orthogonal subcarriers. In summary, the discrete Fourier transform is providing a natural basis for the vectors that we obtain when sampling time domain signals. And it is revealing that these time domain vectors can be described as a linear combination of complex exponentials with different frequencies. And in a communication system, the discrete Fourier transform is particularly useful when studying the received signal when the transmitted signal is filtered by an FIR filter that is creating intersymbol interference. But that intersymbol interference is disappearing when we add a cyclic prefix and turn the whole thing into the frequency domain.